So we might have more people coming in, but the most important ones are here. So, so today's guest, our distinguished speaker, is Professor Satish Ukkusuri from Purdue University. I've known Satish from his days at RPI, and he's not a stranger to New York City. He's done a lot of great work for New York City and New York State. So he knows our network very well, our problems very well. And he's been, how many years? 10 years in Purdue?
9 years.
9 years. And he has a wide range of projects. I worked with him on a couple of very interesting projects, from OFAR deliveries to evacuation emergency management. So we kind of know each other very well. But I think today he's going to show you things that I also don't know in that detail. So I'm looking forward to his talk. And with that, I'll just leave it to him to talk a little bit more about what he is doing lately and all the great things.
All right, very good. Good afternoon. It's a pleasure to be here. As Carl mentioned, I worked in New York State for 4 years before going to Purdue. So some of the topics that I talk today will relate to New York City. But I want to kind of paint a big picture about big data, smart mobility, some of the work that we have been doing over the last 10 years. And a lot of people have been doing in the space. But I want to talk about convergence of these networks with smart mobility technologies and big data. So the work which we are doing in my lab with my students and postdocs over the last 10 years. So my talk is divided into 3 parts. Motivation and the drivers of what are some of the changes that we are seeing in this space. Then looking at convergence, talking about one idea in more detail about this convergence of networks and big data. And the third part is looking at some ads, showing you examples of some projects that we have done in the past related to big data, right? So using various kinds of data sources, from social media, from mobile phone data, from GPS traces of taxis, and so on, and then kind of give you some directions of future research and trends in this space. If there's time, we'll also talk about autonomous vehicles, right? So I have a lot of things that I want to cover here. So the time will be when we reach about 15 minutes or so, we'll just stop, okay? And I'll take some questions from you guys. Okay, so we have been hearing a lot of things of shared mobility, right? So Uber, Lyft, different kinds of ride-sharing apps, bike sharing. Then we have apps for travel time prediction and estimation, self-driving technologies, apps for disaster management, Internet of Things, and so on. All of these things are driving cities and in terms of providing services to people, but more importantly, connecting cities with services, the citizens that are there, and the services that they need with agencies in the cities, right? So, if you look at this space, various industries are also participating in this. IBM, Cisco, and Accenture examples, right? Where they call smart cities. But the key idea here, if you see the commonality of these definitions, is this integration of information from various kinds of sensors, right? From sensors in space and time, right? Which provide us information about where people are, what are they doing, how much time do they spend on these various activities. And the second piece is these communication technologies connecting citizens to the service providers, which is city agencies, NIMTEC, New York State DOT, right? And various types of city services. So this connection is what's been missing over the last many years, right? And then the third is to provide value from this kind of data in terms of reducing congestion, improving air quality, and many, many other things, as we will see in today's presentation, right? So these are some commonalities that we see from whatever definition that we actually take from industry or agency in this wide space of smart cities. Now, why is, okay, so there's a delay between these two. So let's look at some of the drivers. So before we're going into the presentation about specific research topics, let's look at some of the drivers of what changes we have seen in the last 10 years, right? So Professor Osbe and we have been in this field I've been in this field for about 17, 18 years, and we have seen these trends in the last 15 years, right? And in the last 10 years, when I started this research on data science, I'm most of a networks person, right? Most of my work is in dynamic networks, static networks, primarily for transportation. But when we started looking at this data on networks, right, last 10 years or so, there's some fundamental drivers that actually relate regarding the initiation of these kind of changes. The first driver is this penetration of smartphone, right? So when I used to give this presentation almost 8 years back, I used to show a smartphone to everyone. I don't do that anymore, right? Because everyone knows what a smartphone is, what an app is, and so on. So by 2019, 1/3 of the population of this earth is going to have a smartphone. And what are they doing with that? They're sharing their data, they're sharing their location, they're sharing information, they're communicating with people. And all of this data, every second, is being recorded, is being shared with service providers, right? And people are using this for various kinds of services, right? For getting groceries, for shopping, for traveling, right? Health, for getting pharmaceuticals, and so on, right? For every service, there's an app out there, right? How many of you sleep with your cell phone next to you? I do, right? So we can probably live with water or food for a day, but not with our cell phones, right? So we are so much dependent, and this is a recent trend. This was not there 5 years back, 10 years back. We are so much dependent on these technologies for various things that we need in our lives. Should probably use this. The second driver is the ubiquity of sensors in cities, right? So if you take a typical car, we used to say, oh, there are about 200 plus sensors. Now it's more than like 400 plus sensors. Why? Sensing has become very cheap. Sensors have become very prevalent, right? So we have a lot of sensing capabilities which provides us high volumes of this kind of data. And communities are becoming connected villages. The third driver is the rapid changes in behavior of people, right? So if you see your parents, right? So Facebook is no longer a younger generation thing, right? It's for grandparents. So all the young people are moving away from Facebook, right? So older people are actually beginning to use these technologies, right, at a very rapid pace. So the adoption of these type of technologies is very high, right? So 12 years back, if you see, very few people use Google Maps for turn-by-turn navigation, but almost about 80% of people now use these type of navigation apps. 11% use their phone at least occasionally to reserve a taxi or car service, and this is 2014 data. Now it's probably much higher, right? So these type of behavioral changes and the adoption of these technologies is increasing very fast, not only in the US, but in the rest of the world, probably much faster in Asia and Africa, where they're kind of leapfrogging some of these older technologies, right? So these three main drivers, what is the result of this? This provides us a tremendous amount of capabilities in terms of data. And we can do a lot of things with this type of data, spatio-temporal data of where people are, where assets are in space and time. And these are moving on networks, right? So what do we do with this data? What type of methods, what type of problems can we actually solve with this kind of a data, right? And there is a supply side and there is a demand side for this kind of a data. So what I want to do today is to share with you some of the ideas that we have explored in using this type of heterogeneous data on heterogeneous networks to understand various questions in urban areas, okay? So that's the connecting story behind this presentation. So you might see a lot of research questions, but behind all of that is this bigger question that we are trying to kind of address. Okay? So, what is big data all about? Right? Simple definition, anything which does not fit in your Excel. Right? So as soon as your Excel crashes, you have a problem either with Microsoft, that means you need to reboot your computer, or you have a problem of size. Your data is no longer sufficient for Excel to actually handle, right? So, but a more rigorous definition of this big data is characterized by three things. One, the scale of the data itself, both in terms of the size of the data and the velocity of this kind of a data. The second is the unstructured nature of this data. The data is not necessarily perfect. It has a lot of noisiness in this data and so on. And this data is real-time, streaming over various time intervals and spatial scales, right? So there's a very high velocity of this kind of data. So when you are dealing with this kind of data, it poses new challenges in terms of how to handle this kind of data. Unlike survey data, which most of the transportation students may have used in planning course, right? So where you have a representative sample and so on, and you're trying to make inferences with that kind of data, right? So here we have huge volumes of this data, but the data is not perfect. Okay, so the common misnomer is that big data means so it should be really nice. We should be able to solve our problems, right? But for our problems, especially in cities and for urban transportation systems, need not necessarily be so, right? It depends on the kind of problem you're solving. It depends upon the kind of data set that you have in big data. And so that really, it depends on a lot of factors related to the quality of the data and related to the kind of problem you have at hand. So sometimes small data is actually better than big data for some problems, right? The scale of data and network effects and interdependencies poses challenges to develop these kind of new methodologies. So, but there's a real opportunity here if the problem and if the data set is appropriate for the kind of research question you're trying to address, okay? So, a little bit of history here in terms of transportation modeling. So if you look at transportation modeling, there are two main assumptions we make both on the demand side and the supply side. On the demand side, utility maximization has been the governing framework which we have used on the behavioral side. On the supply side, we have used equilibrium or people choosing the least cost path, right, in the network, right, to make their travel decisions. But when we started this in 1950s, we had very limited amount of data, so there's not a lot of validation. We could not really test these assumptions, right, that we actually made in modeling these problems. Over time, we did validate this with limited amount of data that we have from loop detectors, from surveys, and so on, right? But still, we had many instances where these assumptions did not hold water, right? So we were never able to kind of see what was the alternative mechanism by which the supply side and behavioral side assumptions are governed. What I claim is that we now have an opportunity to actually question some of those fundamental assumptions and let the data speak for itself and write these assumptions in a way that it fits our modeling framework, right? So that's one opportunity which we have been trying to kind of do, to kind of let the data speak and inform the assumptions that we actually make in our models. Okay, so that results in a new kind of modeling approaches, and I mean, I can talk about this philosophy here for some more time, but in the interest of time, if someone is interested, we can talk about that later on. So almost 9 years back when we started this work, the first question we asked was, well, we have a lot of this data from taxis and social media, which we are able to collect from Twitter, but is this data really useful? When we say usefulness, one measure of usefulness is it representative, right? And for transportation people, we know that issue very well. We want this to be representative because we want to kind of scale it from a sample to the entire population. right? So that was one of the first questions that we actually asked in 2009 when we actually started this work. And what we did was, so we actually did look at various sources of data. We looked at various articles related to the usage of these kind of social media tools. And this is one snapshot of this kind of information about age group distribution, mobile phone users, check-ins in Foursquare, right, in New York City. And what we see is in urban areas, so the conclusion from all of this analysis is in urban areas, the data is reasonably representative across all age groups. Cannot be said for the rural areas where I come from, West Lafayette, right? But in urban areas, New York City, Chicago, San Francisco, and so on, there's a pretty good representation between the demographics and the usage that is there of these different types of techniques. There's some underrepresentation above 65, but not too much. And again, this is old data. And the volume of data is significantly high, thereby canceling out some of this noisiness which is there in this kind of a data. You have a question? Okay, so when we develop our models using these data-driven approaches on, especially on networks, all of our models are on networks, right? So we have various ways to kind of develop these models. So I kind of, when I work with my students, I give them few guidelines about how the philosophy behind modeling these problems. The first thing is that let the data speak for itself in terms of the assumptions. Let's not make overly restrictive assumptions on the modeling framework, right? And similarly on the choice of the model, let's be flexible in terms of these choices of this model, right? So there are various data sets that we can use, and wherever possible, you want to integrate these kind of different data sets. And first, you want to be able to clean this data that you actually have, then develop an appropriate algorithm or modeling framework for that, and then estimate this, do the inference, and then the estimation and then testing of this model function, right? So there is a philosophy behind how we actually develop these models for this, okay? So that's my first part of the presentation, which is like a introduction philosophy of why these models are important and how we actually go about doing this, okay? The second part of my presentation, I want to just dive deeper into one specific topic where this kind of integration takes place, okay? And I've been a big believer of this kind of convergent research. And what we mean by convergent research, and I'll just explain that in the next slide. So I want to kind of show you how this convergence between networks, big data, and resulting in new, enriching models can take place with an example of recovery in complex neural networks, which are subjected to various kinds of shocks, right? Shocks of various time durations, shocks at various spatial locations, and so on. So this is some part of my CRISP grant that we currently are working on right now, right? So what we mean by this convergent research is a deep integration of knowledge-based tools and ideas from related disciplines to kind of create new, synthesize and create new theoretical frameworks and modeling ideas, right? This will help us to create new foundations for knowledge, explore questions that are not possible with just one single domain, right? And most of the grand challenges that you actually see today, be it in cancer research, be it in material science, be it in health engineering, be it in infrastructure engineering, right? Can only be done, in my opinion, can only be done by taking this kind of a convergent approach. Because these problems are too complex for a single discipline, right? And recently NSF has been also very focused on this kind of convergent research. And I just found this a few weeks back that NSF is going to focus on this kind of convergent research over the next 5 to 10 years, right? So this is, I feel very encouraged by looking at these kind of directions. Okay, so let me share let's take a deep dive into some of these things, right? So we have data about about the structural properties of various road networks, various pipe networks, various sewer networks in various cities in US and in Europe, okay? And we also have functional properties of these networks. What's a functional property? A functional property is how much of traffic flow is there on every lane, what is the speed characteristics, how much of water is flowing across these pipes, what's the diameter of these pipes, what's the material of this pipe, and so on, right? So for different kinds of infrastructure networks, we have functional properties of these networks as well. So the questions that we are interested are there underlying signatures across physical, natural, social, and human networks, which are common across all of these different networks? Are there some unifying scientific principles that are common across all transportation networks? So one level down, right? So from a more general setting to specific to transportation networks. Do we see any co-location of these networks? Is there a correlation between these different kinds of networks, either spatially or temporally? And the observation of networks of the several road, pipe, and river networks show they do have similar properties, right? So here we show this road and sewer networks, right? Same here. What you see is when you actually look at the degree distribution of these kind of networks, they share a common property at whatever scale that you actually do, in whatever city network that you actually take, right? So they do share, one property that they share is this degree distribution, right? And we have done this with different pipe networks, we have done this with road sewer networks, we have shown that co-location does exist spatially and temporally in some cases, right? Then the question is, once we understand this, once we establish this hypothesis, the question then is, can a new theory be built to understand the failure and recovery of these interdependent networks, right? So if you have a shock in these kind of networks, how does the shocks propagate or cascade within these networks and across these multi-layered networks, and then can we really come up with how these networks would recover over time, okay? So to do that, first we need to understand this idea of what's called dual mapping of these networks. Very quickly, I just want to share with you what we mean by this dual mapping. So dual mapping is a transformation from the original network to a different network and then look at the degree distribution of this network. So this is the original network, for example, road network, right? With nodes representing intersections, link representing roads, right? And then they might have some functional properties of congestion, travel time, and so on. What we do is we do a dual map where the link becomes a node, right? So link, for example, with the same road name, all of them will become one node. And then the node becomes a link, so the node being an intersection or some kind of a relationship now becomes a link in this kind of a network. So we transform this so that why do we do this? So that we actually can look at some common attributes to see the hierarchy, if there's a hierarchy in this kind of networks. So the dual networks no longer have planar embedding and are able to uncover the hierarchy. And the important links in this network would have a large node degree in the dual map. So if you take, for example, Manhattan here, right, that's the primal graph, and the dual graph would look something like this. So all of our analysis, this is much more easier to understand and handle because now we are talking about the importance of some central nodes and links in the network rather than if, for example, there might be an important arterial but that's broken into like 50 different links, and that will not tell us anything about the properties that that network has, okay? So, the first important result is this one, right? So you have various road networks, and what do you see of this degree distribution? And this degree distribution is all done on these dual graphs. So you see that they all share the same kind of degree distribution, right? So it's truncated. In some cases, it's truncated here, but they all follow a power law distribution, right? So that means it establishes that there's a hierarchy in these kind of road networks. There are main arterials which are connected to the secondary arterials, to the local arterials, and then the local roads. So there's a strict hierarchy. So some links actually carry a lot of traffic, right? And so this is the 80-20 rule that we see in many different networks. And we have done this analysis with many different road networks. The second thing is this true if we reduce the scale, right? Is this true if you reduce the scale? So we have done a scale analysis. That means if you take Pittsburgh, you only take the entire network, or 1/4 of the network, 1/16 of the network, or 1/64 of the network. Does it establish a similar property? And we see that, yes, it does. It actually does have this scale-free property across these different resolutions of this network. So we see that that's a very important property in these networks. Then after that, what we do is how can we predict these kind of functional failures on flow-based kind of networks. So if you have flow-based networks, like road networks being one good example, how can you look at the incorporate both structural failures, like for example, what happened in Atlanta, right? So there was a link, there was a road on the bridge which got damaged, caused huge congestion problems in Atlanta. That's a structural failure for a few days, right? But you have functional failures due to accidents, due to over-congestion, and so on every day. But typically, we do not really account for those things in our modeling process very well. So the question is, how does this functional failures cause cascading in these networks? And can you predict which links are going to spread, when it is going to recover, and so on, right? So these are some of the questions which we are interested in terms of understanding the network structure and functional properties. So using the idea of that dual mapping, okay, and a data-driven approach, we combine these two to understand this problem of this congestion evolution and the cascading behavior on this network. So we have done this on two big networks. One is Beijing network, the complete Beijing network, and the other is the Shanghai network, okay? And the way we collected the data is, since Google Maps is not popular in China, we collected using Baidu Maps, right? So Baidu Maps, we actually use the web data crawler to collect the travel times on every link in Beijing and Shanghai networks at the resolution of about 30 to 40 minutes, okay? For about 6 months, we actually collected this data. And so we have the state of the speed information of every link in the Beijing and road network. And what we do is we take that network every 30 minutes, right? And we transform it into the dual graph. And the dual graph here, the function is the state of the link, whether it is congested, medium congested, or low congested, right? We transform that into the dual space. And if it is very high congested, that particular node is going to be split. It's going to come in the next slide. It's going to be split, right? And that tells us that how it is going to actually cascade into this kind of a process. So the implications of this is that disappearance of high dual degree nodes tells us the state of that particular link, and dual degree nodes distribution reflects breakdown of this original hierarchy. So I'm going to play a video here using all of the data that we actually collected. So this is the Beijing road network. We have the different ring roads here, so you can see the ring roads, right? All the ring roads here. So I'm going to play the video. What I want you to observe is how the color of this graph changes and how the slope of this distribution actually changes. So let me first explain this base, the blue line, which is the base dual graph. The base dual graph distribution is when there is no congestion in the network. So that's the best you can actually do. That's the best degree distribution.
Can you read the axis and the ordinate in there? What are the units?
X, Y.
The X, Y.
This X and Y axis?
Yeah.
So this is the node degree, and this is the probability of having that node degree. So this is a PDF. This is a probability distribution function. Right? So this is when there is no congestion in the network, and this is when there is some congestion in the network. So I want you to observe when I play this video how this red line is actually going to change, and tell me if you observe anything interesting here. So this is the timestamp. 9:10 in the morning, 9:45 in the morning, and so on. So anyone? Any volunteer here? What do you observe?
I noticed the PM is pretty congested in the central
Right.
area.
Right. So as it's getting congested, what's happening? This red line is moving away from the blue line, and as the congestion is reducing, it's kind of coming back closer to the blue line, right? So that's a clue into what's happening, right? So that means the degree distribution, the slope of it, tells us something about the state of this overall network. As you have more congestion in this network, as more functional failures happening in this network, this degree distribution is going to be away from our base degree distribution. And that tells you, so the slope is going to be an indicator of how much functional failures are happening in this network. So that's an important insight we can actually get from this kind of a problem. And we have done this in, as I mentioned, in Shanghai network as well, right? So now we can put a theory around this. We can put some very nice theory around this using both networks and big data, right?
So
Yeah.
So it was happening at the, mostly at the tail, no? I mean, at the lower probability.
Right. And there is also a reason for why it actually happens at the tail, because this is primarily being influenced in the major roadways in the network, right? So the ring roads, for example, are going to get more and more congested. So you're going to see that. So it's happening around from here to here, right? But mainly you can see this difference in this part, because the ring roads are the ones which get severely congested during the peak hours. So based on these insights, based upon all of this data analysis that we actually do, we can develop a very nice model to predict which roads, if there's congestion in some parts, which roads is it going to propagate to, and how much time will it take for it to recover back to a normal process, right? Using the dual theory. So this is the normalized split probability distribution. So we're going to split these dual nodes. This is the PDF of this degree distribution, and this is the negative exponential distribution of how much time it would take for a node split to recover back to this original form, right? So we can get this empirically from all the data that we actually have, and what we do is we develop both a microscopic and a macroscopic model to determine which nodes are going to likely split, and if a node splits, which of the neighboring nodes are going to actually split, right? What's the likelihood that the neighboring nodes are going to split? And we can characterize this kind of a splitting probability using this Markov chain process. And so there are 4 sub-modules in this process. One, self-splitting, whether a given node is going to split or not, right? And it's a function of the traffic load that is actually going to be there. And then self-contagion, which is the congestion are more likely to propagate along the same road. And neighbor contagion, which is the congestion is spreading to the neighboring roads. We can predict that. And finally, the recovery, which is if a node splits, how long is it going to take to recover that back to the original state that we actually have, right? So this is the very nice simple equation one could write to determine this self-split rate, the self-contagion rate, and then the neighbor contagion rate. And some of these parameters are estimated from the data analytics that we actually have done, right? And the insights of that PDF that we actually saw so far, right? So once we build this model, you can see we can use it for prediction purposes. So you can actually predict the likelihood of the spread in this kind of a network. And we have done this for different time intervals and different loadings. We have done this for weekday and weekend in December 2015. This is for the Shanghai Road Network. We can do it with different weights given to those 4 parameters that you actually saw in the previous slide, right? And you can see that there's a very good agreement between the data and the model, right? So this is, you're bringing in the data, you're bringing in networks, you're bringing in the transportation knowledge, everything into this to understand. So it's a physics-based model to understand the recovery of road networks, but also to understand where this spread is going to happen, right? So one thing which is interesting is we have not really put a lot of assumptions that, oh, people are going to make these kind of choices, right? It's not transportation heavy in terms of these assumptions, right? But some things we need to consider are, we need to consider the lanes, we need to consider speed limits, we need to consider design standards of roads. So those things can be parameterized and put into the model, so we're thinking about that. But the key takeaway, another takeaway I want you to kind of think about is, because the assumptions are not too much heavy on the transportation side, water researchers, they're actually developing similar modeling frameworks in Germany. They're using the same model to understand the recovery of pipe networks and sewer networks, right? So because the modeling philosophy, there's a flow there, there's a function, there's a structural form to these pipe networks and sewer networks. So you can extend these concepts to understand the failures in both pipe and sewer networks, okay? So that's the end of part 2 of my presentation. And part 3 is about some advertisements about work that we actually have done in this data science space on smart mobility. And what I'll do is I'll just spend a minute or two on each project that we have done. And if anyone is interested to know more about a specific research question, just raise your hand, okay? And then I'll be happy to expand upon that in more detail. So, we have worked with different kinds of data sets. We have worked with New York City taxi data set extensively, right? We have worked with a couple of data sets in the US from taxi, GPS data sets. About 6 cities in China, again taxi. A lot of social media data sets in urban areas, but also under disaster conditions. We have used mobile phone data, right? We have again used transit smart card data, and so on and so on. So I'll just show you a sample of some of these data sets. So some of these data sets have geolocation, and geolocation plays a very important role in terms of telling us information about activities which people participate in. It does not have socio-economic characteristics due to privacy concerns. And some of this data that we have collected from social media, right, and Foursquare has missing activities, so it does not, for example, it's social media checking data, but it does not have all the activities because people don't check it. This is the taxi data, right? You can do simple visualizations of this taxi data. Most of you may have played with this kind of a data before, right? So these are the origins of these taxi trips and destinations of these taxi trips. So anyone who has done analysis with this data knows that 70% of the trips come from Manhattan, right? Hotspots in terms of these airports and so on and so on, right? So you can do these kind of simple visualizations from this kind of data sets. One of the questions we have explored early on is in terms of estimating the travel time using this kind of a taxi data, but not just estimating a deterministic travel time, but estimating the entire distribution of this travel time, right? So, as most of you may know, the taxi data set in New York City does not have trajectory information. It only has the pickup and drop-off information. It has the travel time, travel distance, fare, type of payment, and so on, right? But it does not really have the trajectory. So, one of the first questions, we did this way back in 2011, right, is to understand how to predict the distribution for all links using taxis as probes in this kind of a network. So it's again a good combination of network tools and data science tools to kind of estimate these distributions. So without really going into the details, there are some nice algorithmic approaches to boost the performance of these approaches using EM approaches and fast path inference techniques, which we have used in this work. And if you look at these results, they're pretty good. So this is a part of a Manhattan network, right? You can estimate the speeds, both the expected value and the standard deviation of the speeds, right? And you can see that, and we compared this with limited loop detector data on some limited links that we actually have, and the agreement is about 85 to 90% for most of these links, right? And you can see that the average speed during peak hour is about 8 miles per hour in most of these links in Manhattan, right? So you can do this kind of analysis. Then we have also done one very interesting understanding of these taxi markets to understand how taxi markets can be modeled, right? With this app-based, with the introduction of Uber, Lyft, Didi, and so on, and the traditional taxis, they're all in the same market, right? What is the effect of these new entrants on these traditional taxi markets? What is the effect of surge pricing in terms of the choices that people make, right? How do you model this kind of a market and the effects of utilization of this market? So this is the taxi market equilibrium with these app-based taxis incorporated within this kind of a service. And we tested this using limited data from, again, New York City and a few cities in Wuhan, China, and Shanghai, and so on. So you can model this as a game, right? Where there's competition between drivers in TTS's traditional taxi system. ATTS is an app-based taxi system, and they're all competing for the passengers. The surge price impacts the utility of the driver and the passenger, right? And we can model this as a leader-follower kind of a game, right? And the three different kinds of games. So you can have this game one with the driver as the leader, with the ATTS driver as the leader, and the passenger being a selfish passenger trying to minimize his or her cost in this kind of a network. So we can formulate this equilibrium properties of this game. You can kind of show some properties about the solution existence in this kind of multi-leader follower games, right? The hard part of this is how to solve these kind of games, right? How do you solve these kind of games efficiently is something which is a little bit challenging. So you can compute the equilibrium for these kind of games, right? Equilibrium is the utilization of these different sets of passengers in this kind of a game. And you can look at the effect of the surge price. So the surge price you can see on the x-axis and the total passenger cost on the y-axis. You can see the effect of computation, right? So the red is the app-based taxi, the green is the traditional taxi, and then this is the number of passengers. As the cost here, the surge multiplier on the ATTS is decreasing, right? More people are more likely to actually move towards the ATTS. You can see that kind of computation, how it plays out in this kind of a system. One result which is important is we find that the surge price multiplier of 1.2 gives the most competitive market. This is the tipping point really when people kind of move from the app-based to the traditional taxi system. Recently there's a paper by Uber with some economists, right, where they have used a lot of Uber data to understand this question, and this number is exactly what they got. 1.2 is exactly what they got from all of the analysis of the surge pricing data that we have. And this is published, I think, in the American Economic Review with some economists that they have actually done. So last week, Uber introduced a new system called, right, where you actually need to walk a little bit, wait a little bit, and then do group rides in terms of using Uber app, right? Uber just launched that last week. The same idea is there in this paper, and this was done like 3 years back, in terms of the optimal assignment an incentive design in a taxi group ride. This is not ride sharing exactly, but this is taxi group ride. Actually, New York City had this, I think, in 2010, where the traditional taxis, they had various stops where people can wait and they can do group rides, right? And they abandoned that, I think, in 6 months or a year. So what are the locations where people can pool together, right? Wait for a taxi and go together to some common destinations. They need not go to the same destination, but they may have to walk a couple of blocks. The motivation for this research question is this evidence that we actually have from New York City taxi data. 83% of passengers can find at least one group ride if they walk quarter of a mile and wait for 2.5 minutes. That means we can eliminate 83% of individual taxi rides if people are just willing to wait, right? 2.5 minutes and walk a little bit of a distance, couple of blocks, right? This evidence actually helps us to model this kind of a incentive mechanism for doing this kind of group rides. So there are interesting network problems here as to how do you group these rides, what locations do you do that, how do you determine the price of this group ride, right? So all of that is there in this kind of a research work that we actually have done 2 years back. The problem is also interesting from a mathematical point of view because these problems are very hard bipartite graphs, and so kind of solving them at very large network sizes become very hard. So we actually did develop some heuristics to actually solve this, and you can see our exact algorithm, the greedy algorithm, and a heuristic, and heuristic actually gives pretty good performance for these kind of problems. Okay, all right, so I'll just quickly talk about some ongoing work in the last few months. So we have been collecting data from Uber. I mean, I gave a talk at Uber a few years back, and at Lyft a few years back as well. We had conversations about data sharing, but really we did not really get any data, specific data useful for research except for trends, right? So what we decided finally was that we were going to collect the data by ourselves from Uber app. And so what we did was a group of students and myself, we actually did develop a hack into the Uber app, and we put in some virtual stations. Let me see if that's there. Yeah. So we put in some virtual stations, data collection stations. As you can see, all of you know this map, right? We put about more than 470 stations. We collected this data from April 7th to May 2nd from various Uber IDs. So we have a lot of, about 100 GB of data per day from Uber, right? So we have a lot of data from Uber, which we have been kind of analyzing. So this is all data which tells us, again, information about pickup, drop-off, right? The fare, whether there's a surge multiplier, and location, and so on, right? So we have actually done a lot of analysis with this data after the summer, right? So if you're interested, keep an eye for this, right? I'll talk about that in a future presentation sometime, okay? We have also done a lot of work with social media data, with Twitter data, right? So we have used this data for understanding activity patterns in cities, doing urban activity pattern classification, right? So this is something you can actually read, published in Part C. We have used this for disaster analytics to understand sentiment in disasters, to see what concerns people have at what time, how these concerns are evolving with time, right? So this Oklahoma tornado is one example. We have also done this in Hurricane Sandy. Inferring land use. So we have used the Twitter and Foursquare data to infer land use. This is the actual land use pattern in New York City, and this is the inferred land use from both the supervised and the unsupervised learning algorithms that we actually have developed to predict land use. And of course, we have done a lot of work in social networks and disasters, starting from Hurricane Sandy. More recently, we've been collecting data from Hurricane Matthew and Harvey. Right, so this Hurricane Sandy, we have about 52 million tweets, almost all the data from 13 million users from October 14 to November 12 of 2012. Right, so we have been kind of building the social network. The fundamental question we are interested here is how does influence work? How does the people that you are connected to in the social network influence your decisions that you actually make, right, on a day-to-day basis, whether you evacuate or not, what time you evacuate, what mode you choose. So how does your social network, who you are connected to, the quality of those connections, and how does that influence the decisions that you actually make and the risk you actually take, right? And that's what really we are trying to understand in some of this research. I think I'm almost out of time. I think I see it's 3:22. Okay, so this is all the autonomous vehicle stuff which we are doing, so we'll skip that. We are developing a roadmap for this autonomous vehicle for Indiana State. Okay, so this is my final plug-in for you guys. So this is a book which is just coming out, and this is Transportation Analytics in Big Data, right? So this is just being released, I think, this month or next month it's going to be out. So if you're interested in knowing some of the recent emerging trends in this area, you can look at this book. I'm a series editor for this Elsevier book series on smart mobility. So we are putting together a few books in this year and next year. So I see a few experts in this room who could be potential editors for these books. So I'm going to talk to them after this presentation, right? And with that, my key takeaway, I see some students here, right? My key takeaway, if you're interested in this area, is you need to be comfortable with the unknown, right? You need to be comfortable with really getting your hands dirty and messy with this kind of a data, right? So most traditional transportation students do not have training with handling this kind of a data because either they are not familiar with machine learning, data mining, right? They're not familiar with coding skills. They're not very good on fundamental math in networks and optimization. So if you are really interested in this, you need to really learn those kind of skill sets, right? So one thing which I always say in curriculum meetings is our curriculum needs to be upgraded to actually handle these challenges. We cannot just keep talking about 4-step planning processes. We cannot just stop with traditional safety analysis and so on. Our transportation curriculum should adapt and should update to some of these recent trends, right? And I think that's something which we will continue to do that. But students, you're much smarter than most of us, so I would really encourage you to kind of be creative and go out of the box to kind of learn these kind of skill sets. So with that, thank you very much. I appreciate the opportunity.
Just one quick question about the social network business. So obviously, I mean, there is some, even we see from the president, the elections, there is a big impact. But how do we know, where is the control group? You know, people were not using social networks, for example. And how do we understand, I mean, what is the real effect of these social networks? And how do we design an experiment that will tell us the real impact versus, because you need a control group. In general, you don't have that, obviously, because you're not doing a controlled experiment. So what do you do to address that issue?
Right. That's, I think, a very hard issue, right? Because we really don't have a good control group to kind of see exactly how much accuracy is there in this kind of information, how these people. I think one way to do the control group, I have done that in different contexts, but not in this social network context, is to do experimental games. That means in a laboratory setting, you create these social networks, or you ask people to interact with other people and see the evolution of the social networks, see what kind of information they actually communicate in a more controlled setting, and design the incentives to understand these dynamics, right? And then see how the same similar groups with similar characteristics would perform in a virtual setting, right? For example, you might get their Twitter IDs and so on. So for example, when we do our surveys, we actually ask people to give them, if they want to share their Twitter ID or not. So you can kind of observe their behavior in a virtual setting in a much larger social network and see whether the inferences that you actually get from a controlled setting would match with the virtual setting or not. You haven't done that, and I don't know anyone who actually has done that yet.
I mean, the same question comes on connected vehicle research, like, because, I mean, everything we do with big data, no?
Right.
Because you get the data, but it's not really controlled experiments. So.
Sure. But I think for other kinds of big data, like for example taxi data, I don't think we need a control group
No,
for it.
of course.
Yeah, because that's whatever,
Everything.
that's the
That's
ground truth.
whole-
Yeah,
that's
that's
the
the
whole
ground truth,
universe.
right? Yeah.
Yeah, these big data observations, I think, reflect the reality of how people behave, what they do today. But they don't necessarily address the factors that induce that behavior. And that is very much dependent on, how can you predict the needs for X years from now based on what you're observing today. If you don't know the factors that affect that behavior, then that becomes a difficult thing. So that there is a limit to which these kind of exercises or analytics are really targeted to. They are targeted to the near term, to what can I do to change something or maybe understand what is happening.
Right.
But the near term, however, limits the type of solutions that one can intervene with if you want to make changes that are in the direction that you decide to go.
Right.
The problem is what do you do, in the long pool
Right.
to get out of the problem that we're observing now.
Right. Right.
And,
So
and that's still there. It's not really being addressed by the big data.
So the way I would answer that question is that it's true that the big data does not have some of the indicators that we actually look for in making long-term forecasts in transportation planning. For example, we don't have indicators such as income, demographics, the family structure, all that kind of information. But the point is that we don't perhaps need all of that kind of information, because if you go back to 1980s and look at the forecasts to 1990, 10-year forecast, 20-year forecast, that pretty much all of them are wrong by 70, 100%.
But that's because they did not include the political and institutional aspects of it.
But no one knows the political institutional aspects in the long term.
So that also makes it more constrained to look at the present when you look at the
So
data.
my
You don't include the
my
institutional
response is,
component.
all of these long-term forecasts that people make are completely not accurate.
I would like to see big data applied
Right.
to how I would like to see big data applied to how the financial resources are being gathered, how investment decisions are made. Well, where is money going to?
Right.
And what is the
And
relationship between
in
that?
transportation, I don't know anything that is actually being done. But in banking, in finance, there are some people who are actually looking at that. They're using this to see where money is flowing, what type of investments are hot on a given day, and so on, right? But to address your first question, I think when you have this volume of data, you can correlate it with indicators of macro indicators. Like for example, when you're doing planning, you can correlate with the GDP growth, you can correlate with land use changes, you can correlate with the transit density that is there in a given zone. So there's but not individual level indicators, because we don't have that in most of this kind of data. But my point is that any long-term forecast that we actually make is not precise, it's not really accurate.
Yeah, I understand that, but basically you're talking about existing behavior and not predicting behavior.
I think,
that problem
But
is still there.
over time you accumulate also.
but I think you can
The
learn. I
behavioral
mean,
change.
there's an aspect of learning in these kind of problems. But any prediction, right, is so that is the important thing, which is any prediction is we fall flat on the face when we actually go and see the
It's
reality.
very hard to predict the future.
Because we cannot predict some of these unknowns.
Yeah.
The unknowns being political changes, technological changes that are happening. We can predict, we can learn some things from our historical data, but we can't put in the unknowns that are there. So there's uncertainty and stochasticity completely different.
So those of you who are interested in that, there's a professor here, Nassim Taleb, who wrote the book called
The
Black Swan. So Europeans felt like
Absolutely, right.
the swans are all white,
Right.
Until they went, I think,
Yeah.
New Zealand.
It's
so
like black swan events, so we cannot put it in there,
But
right?
if
And
you
so-
haven't seen it, you cannot predict the black swan. So that very long-term prediction is very difficult.
That's right.
No, the point I was, I'm trying to address is that the big data enriches our knowledge of existing patterns and existing uses, but beyond that, it doesn't allow us to make better decisions for future needs.
I mean, that's
There's
true
a limit there.
Four-step process is not better.
I'm not talking about being better. I'm just saying that there is some limit, because the implication is that big data
There's a limit in
is going to
terms
give
of
us all
course.
sorts of new possibilities.
I mean, I think this all of this data analytics, the limit is essentially what you put into the model.
Yeah.
And what you cannot put into the model is some of these black swan type of events, right? So the model is only as good as what you actually put into it. And the nice thing about this big data is you have the evolution, you have the longitudinal data, you have the dynamics associated with how these things are changing. And those are very useful for short-term forecasts, but also near-term forecasts, but certainly not very good if you're trying to forecast 10, 20 years down the line.
There's also a new center coming up at NYU. It's called AI Now. So basically they're looking at the data and the biases in the data. Because what you observe comes with the biases that people have currently. So
Right.
I mean, it doesn't mean that everything that you learn is really good. So I mean, you learn what you observe basically. So there's a lot of problems with this big data, but it's much better than not having anything and then not.
It's better than no data.
Yeah, exactly.
Yeah, just to add to
And it's
this,
different than, for example, cosmologist or somebody observing the nature, because it has its own dynamics. Here, there's human beings, policy, and so many things. So, I mean, it's very complex. That's why complex system.
yeah, I mean, just to add to this discussion, I think one of the advantages of having that big data, even for long-term planning, is that you can be more adaptive, right? So that you can be more responsive. Even looking at one of the examples on your slides, you showed the ability to model the land use patterns. And so, if we currently follow the way that we're operating right now, we take very long time to adjust our land use codes, right? So like when currently the trends for parking in households in New York City are shifting very drastically, but then the city government doesn't really respond as readily for that. But if we're making use of big data, we could make those kind of adjustments. So I think there are advantages to making use of the big data for these long-term trends. But to the point about like these forecasts for the future as well, you were saying how there's these big confidence intervals in the predictions, and there have been studies that looked into, in hindsight, into all these studies over the years, and I think they found that for predictions for like traffic demand tends to be less unbiased, like more unbiased, and around like 20 to 40% or something like that. Whereas like for rail projects, because there's a lot more lobbying going on, that the politics involved and institutional kind of processes in place, that they cause more bias.
Underestimate the cost.
Yeah, so I think that's something that we do need to work on better to address.
Yeah. But I mean, to Joe's point, I mean, today most of the decisions are also tactical. So this kind of data and this kind of approach allow you to make those tactical decisions, especially like a country like the United States, because I mean, new things are not built that often. So basically, operational decisions are very important. So it allows you to make those operational decisions in a very effective way. I mean, if you go back to China or India or Turkey, whatever, things are changing so fast.
Right.
I mean, no model will work, no data will work probably as much as, I mean.
As long as you put in the decision making.
Exactly.
As long as you put in the rapid decision making.
I had another follow-up question. One of your last points was about the need to update the curriculum. Do you have any suggestions on what kind of short-term immediate changes we can try to implement in our our curriculum to take advantage of these emerging trends?
I mean, I think that's a longer discussion, but I think some things that I have been thinking about, and I think we have been trying to do is to introduce at the undergraduate level itself, like a 1-credit course related to smart mobility, which is taught by a team of faculty who are working on these kind of problems and showing to students that transportation and civil engineering is not just about developing concrete design codes or doing highway design or pavement design, but it's beyond that, and there are all these emerging things. I think it's showing them the excitement that is there right now to be a urban mobility researcher, right? And so we are doing that at the introductory level at the undergraduate level, right? At the graduate level, we have actually developed a couple of new courses. I'm teaching one of them on the smart mobility, where we actually do introduce. We tie it in, it's not an independent course, but it builds upon the network analysis course, which we already have, and ties it in with how these concepts are related to solving some of the problems in computation, right? And teaching them some of these foundational principles of doing data science. So these are some of the things that we actually try both at undergraduate and graduate level. But yeah, there are a lot more things we have been thinking about. We can talk about that.
Any other questions? So with that, thank you again, Satish.